Hi guys, in this video I'm going to show you how to examine the symmetric of polar equation. So first of all, you have to know what's a polar equation. So a polar equation is an equation that is in the form of r and then theta, and then which r is the distance between the center to any point in the space, and then the theta is an angle counted from the positive x-axis to that point. So let's say you have a point here, point P. So r is the distance from the center to that point on the space, and then theta is the angle between counted from positive x-axis to that point. So this is an example of a polar coordinates. So the polar coordinates, they are going to form a polar equation. So now let's consider a symmetric about the x-axis. So we're going to consider three symmetrics. So the first symmetry is a symmetry about the x-axis. Second one is a symmetry about the y-axis, and then the last one is a symmetry about the origin. So the symmetry, now we're going to consider the symmetry about the x-axis. So the symmetry, if we say something is symmetric about the x-axis, it's symmetric about the x-axis if and only if the x-coordinate of that point doesn't change while the y-coordinate change from negative to positive. So if let's say now I have a point here that I will call this point N, and then I have another point here, I will call this point P. So I have point N and point P. These 2 points share the very same x, and then the y here, this y, and then this y here is going to be negative. This is negative y. So the 2 points are symmetric about the x-axis. Why? Because the x value doesn't change while the y value change from positive to a negative. So that's a symmetric about the x-axis. So if I can draw a line from here, from the center to that point, and then draw a line from the center to this point here, as I told you that a polar coordinates is a coordinates in the form of r and theta, and then which r is a distance from the center to any point in the space, which is this r here, and then this is r there. Then a theta is a angle from the positive x coordinate to that point. So this is theta here. So if we count anticlockwise, the theta is positive, but if we count anticlockwise, the theta is negative. So here that means I'm going to have a negative theta, while there I had a positive theta. So these 2 points are symmetric about the x-axis. So if you are given any polar equation, how to examine whether that equation is symmetric or not, So let's say consider now example of a polar equation. Example of polar equation is like r is equals to cos of angle theta. So that's an example of polar equation because it's in a form of r and then theta, with which are variables of our equation. And then if I replace this theta here by negative theta, why? Because these 2 points are symmetric about the x-axis. So if I replace theta with negative theta, and then I get the very same value of r, therefore my equation is symmetric about the x-axis. So let's try. R is equals to cos of minus theta. Then the cos of minus theta, remember that here the cos is positive, here tan is positive, here sine is positive, here all of them there are positive. So here, since cos is positive on a fourth quadrant, therefore I will get r as a cos of what? Of theta. Therefore I will say that this equation is symmetric about the x-axis. So let's try another one. Let's say r is equals to sine of theta, and then I replace my theta with a negative theta, the negative theta. Since the sine is negative here, I will get minus sine theta. And then this, the second one, this is not symmetric about the x-axis because the equation that I get here finally is not the same one as the initial one. So here, these two things, the final one is the same as the initial one. whether the theta is negative or positive, the r doesn't change. So here, if the theta is negative, r changes, so therefore it's not symmetric. So I hope you get that. Then we're moving on to the next symmetric. So the next symmetric is a symmetry about the y-axis. So symmetry about the y-axis, still we're going to apply the very same procedure, but this is inversely of this one, because here if a point on this one is symmetric about the x-axis, the x value stay the same while the y value change from positive to negative, so it's going to be opposite of this one. The second one, the y value stay the same while the x value changes from positive to negative. So let me increase my sketch. Then let's say I have a point here, and then I still call that point, I say this is point N, and then I also have another point here, and then I still call this point P, and then these 2 points share the very same y value, but the x now is opposite. The x value here is going to be x, and then here is going to be minus x, so it's opposite of what we did first time. Then these 2 points are symmetric about the y-axis. So if it are symmetric about the y-axis, here this is theta, and then also this angle here is theta, but the angle that we want to consider is angle that is counted from the x-axis, positive x-axis, to that point. So this point is correct for point N. This is the coordinate that we are consider, but this one is not. Why? Because we want to check the angle from the positive x-axis to that point. So therefore, remember that the whole of this here is pi, which is 180. From here to there is pi, which is 180. Therefore, if I consider the whole of this again, I will get 180. Then if I can take that 180 minus theta, I will get the angle that is left. So the angle here, this angle here is 180, which is pi in radians, minus theta. Theta is this one, so it's a 180, which is pi minus theta. So therefore, to examine, let's consider this example. R is equals to sine of theta. So sine of theta, which is going to turn to pi minus theta. We are replacing theta with pi minus theta, and then if we get the very same results, therefore the equation is symmetric about the y-axis. So let's see. Remember that this pi minus theta is found on the second quadrant. On the second quadrant, sine is positive, so therefore this is going to be sine of theta. So these two things, this equation here, the last one is the very same equation with the first equation. Therefore, this equation is symmetric about the y-axis. So let's consider the last one. The last one is symmetric about the origin. So if something is symmetric about the origin, that point is absolutely opposite to the reflected point. So if we have a point N here, and then we must have another point here, P. So these 2 points are symmetric about their origin, because this point P starts here at the origin, and also this one starts here at the origin, and then both make an angle of 180, which is pi in radians. So therefore, these 2 points are symmetric about the origin. So to examine whether this point, the equation is it's symmetric about the origin, we are going to do this. Remember that here we must find the coordinates. So this is r, remember, doesn't change. Then we count this, which is going to be theta, and then now you have to consider this, because this is the angle for point P. So for point P, it's going to be, remember that I said this is pi, from here to there it's pi, and then when you add this, it's going to be pi plus theta. Then therefore the whole of this angle here, the green one, this green one here, is going to be pi plus theta. So these are the two things that you're going to use to examine whether the equation is symmetric about the origin or not. So let's say you have r is equals to tan of theta. So to examine whether this equation is symmetric about the origin or not, you have to replace theta with pi plus theta. So r is equals to tan of pi plus theta, which pi plus theta is found on the third quadrant. Yes, pi plus theta, and then which tan is positive on that quadrant. Then therefore this r is equals to tan of theta, which is the same as the previous one, as the original one. So therefore the initial equation, the initial one, is symmetric about the origin. So let's consider the last one. Let's say you have r is equals to cos of 2 theta. Then if you have r is equals to cos of 2 theta, therefore r is equals to cos of 2 open bracket pi plus theta. You are replacing theta with pi plus theta to check whether the equation is symmetric about the origin or not. Then this will give you cos of 2 pi plus 2 theta. Then if you got that, therefore 2 pi plus 2 theta is on the first quadrant. So on the first quadrant, all of them are positive. So this is the same as cos of 2 theta. So therefore the equation is reflected, it's symmetric about the origin. Then we are done. See you next time.